Yes, so thank you very much for the kind introduction. Thank you all for being here. Big thank you also to all my co-authors. You see there's rather a lot of them. We'll get to why there's so many in a second. But first of all, to check if you're still awake, who of you recognizes this test? Quite a few, very good. How many of you ever done one of them yourself? Quite a lot, good. So you can really get into the mindset to understand what's going on in this presentation. So for those of you who don't know this is the double cantilever beam test. It's used for mode 1 fracture toughness determination in composites or in adhesive bonds. And you can do it both in quasi-static conditions or as a fatigue test. Now, for the quasi-static case, there are standards available, both from ASTM or from ISO, depending on your preference. But for the fatigue test, we don't have any standards available. And that's not for a lack of trying. There's been quite some efforts, both from the E6-TC4 community, also from the relevant ASTM community, trying to produce these fatigue standards. And the reason we don't have one yet is variability, scatter, or a lack of reproducibility between different labs when we do a round-robin test. So there are still efforts ongoing. There's actually an E6-TC4 round-robin running at the moment. But all of the efforts so far have mainly aimed at how you do the test, what load cell you use, exact procedure, and so on. But as those who've done the test themselves can tell you, there's also some subjectivity and some different choices you can make in the analysis of the data. Right? So that leads us to the question, okay, is the variability coming from the test or is it coming from the analysis? So we decided this E6-TC4, let's do one of our favorite activities around robin, but then on the data analysis. Right? And look, how do these subjective choices, how do these differences in how you approach things affect the crack length measurements, the crack growth rate measurements, and eventually the Paris curve, which characterizes the fatigue properties. So we got together a team from 6 different institutes. You can see them over there. One institute supplied 2 independent analysts, so 7 analysts in total. And we set out to do this round robin. And what we started off with, we took some data from a single test done at TU Delft. I need to emphasize this. Everything you're going to see is from one single test, the same data, only analysis is different, right? But same test. So this was a double cantilever beam test on a carbon fiber epoxy prepreg done according to the draft E6-TC4 protocol. On the displacement control, our ratio 0.1. And we had a camera aimed at the side of the specimen. So every so often we took a picture where you can measure the crack length. So we have a millimeter scale here. You can see the crack tip over there. And every cycle, we have a maximum and minimum force and displacement measurements from the fatigue machine. This raw data was sent to all the participants, and they were then asked to produce a crack length curve, a crack growth rate curve, and the Paris curve. So let's dive straight into the results. In view of time, I will go a bit quickly through some of them. Here we see the crack length measurements, and you see between the different participants, a spread of about 1.5 millimeters in the measured crack length. Again, same experiment. Right? This is just how did people interpret the pictures and how did they do the processing of that afterwards. Right? So you think, 1.5 millimeters, not so much, right? The ASTM standard for the quasi-static test specifies you need to have a precision of 0.5 millimeter in your crack length determination, right? And all of this, of course, works in the further analysis. So in the crack growth rate, here we start to see some real differences in what people did. So a number of labs fit a single function through the crack length curve, then took the derivative and so you get a very nice smooth crack growth rate function. Other labs took a secant method or the polynomial fit method from ASTM E647. Right, we take 7 points, you put a second order polynomial, you take the derivative of the center point, and that's the crack growth rate of the center point. You repeat. And so you can see if you take that approach, then you get kind of the same general trend, but you're oscillating around the general trend found by the single curve. Right. A number of labs also tried the secant method, and what we probably already knew, with modern techniques where we have lots of crack length measurements, the noise of the crack length measurements overwhelms the crack growth rate between two measurement points. So the secant method just doesn't work. It goes all over the place. You get negative crack growth rates. Doesn't really make sense. Then the real meat and potatoes, the Paris curves. This is a factor 100 in predicted crack growth rate for the same Gmax value. 100. Not so good. So we do see some clustering, right? So we have labs B, D, and E relatively close together here, A and C relatively on top of each other, and then lab F a bit further away. And if you look into the labs use different methods to predict the strain energy release rate, and especially for lab F, they use this theoretical equation, which relies on a datasheet value for the Young's modulus. And in fairness to lab F, I have my doubts about that datasheet value, right, compared to the actual specimen we had. So when we looked at this, said, okay, that's quite a big spread. Can we make this better by making more consistent what we're actually doing? So we ran a second round of our round robin. And in the second round, we did two things. We gave everybody the same crack length curve, specifically the one determined by TU Delft. Not claiming that's the best one, but we just wanted everyone to use the same one. And similarly, we specified all participants to use the modified compliance calibration method. Again, we can have a separate debate whether that's the best method, but at least everybody's doing the same thing, right? And then, okay, looks better, right? So lab F is now agreeing with B, D, and E. A and C is a bit more subtle, but they're now really on top of each other, where they were slightly shifted in the previous one. But still, there's the spread. So looked a bit more detail, what's going on here. And we found a difference in how the compliance was being calculated. Right, so lab A and C took the maximum displacement over the maximum force. The other labs took the difference between maximum and minimum displacement over difference in maximum and minimum force. And to double check, is this really the source of the difference? We reanalyzed the data for lab A and C, and lo and behold, they then fall on top of each other, right? So this is looking pretty good. So say, okay, yeah, we need to specify what we do. You see some differences between the labs that used just a single curve to get the crack growth rate, and the labs used iterative method, right? So there's a bit more noisiness, a bit more messiness. That's not to say that that's wrong, right? So you can question if you have these nice, straight, smooth curves, whether you've not smoothed out certain variability you do actually want to capture, right? But the difference is there. But still, you can ask, okay, how good are we now, right? How close is this actually together? So for that, I did the following as kind of a rough way to estimate this. I fit the Paris curves through this data, and then I looked for 4 values of Gmax. What is the difference between the maximum and the minimum crack growth rates we get out from those Paris curves? And you see there's between a factor 2.5 and factor 4.5 difference in predicted crack growth rate for a given Gmax. Again, from the same experiment. And even if you look only at lab B and E, which were the most consistent in the approach, you still see a 1.5 to 1.75 factor difference in minimum and maximum predicted crack growth rates. Probably we're now down to rounding errors or really details of how the fit was done. Another question is, okay, how does this compare to the scatter we've seen in previous round robins? So this is the work of Stephan who led the previous thesis round robin. And then if you look just qualitatively, in the first round, so where people are already doing different things, it seems to be about the same order of magnitude as the experimental scatter we see. Whereas if we zoom in on round 2, okay, there is some scatter, but it does still appear to be smaller than the experimental scatter. So it's probably not that this is all down to difference in analysis. So to summarize all of that, we found that it's really important to standardize how you're doing your data analysis, not just how you do the experiments, right? And especially, how do we calculate the strain energy release rates, and how do we calculate the compliance for found to make a really big difference in the results you get. And even if you do standardize everything, we're still left with a factor 1.5 to 4 difference between labs in the predicted crack growth rates for a given Gmax value. So all in all, I think as a community, if we want to be able to compare results between labs, between different papers, we really need to come together and specify some best practices or standards, not just for how we do the test, but also for how we do the analysis. Thank you very much.